just looking at doing just a couple more examples on using the differential calculus to solve a few problems with regards to some graphs of different functions. So for this particular example, we're looking at a cubic, and we just want to find the values of x where the function is increasing and where it is decreasing. So really, we just need to make sure we understand what the question means by that. So just working with sort of a straightforward function like this, at least will help us in terms of just the method to do it. I mean, we could apply it to any kind of function, but with something that's familiar like this, at least it allows us to look at the method. Okay, so regardless of the function, this is how we would do it. Okay, so we're working with a cubic, and it's a positive cubic, so the function we would expect to look like that. Okay, so where the function is increasing, an increasing function is where its gradient is positive. Okay, a decreasing function is where the gradient is negative, because as you're going from left to right, okay, as your value of x is increasing, your value of y, or the value of the function itself, is increasing. So that's what we mean by an increasing function. And it'll be decreasing as it's going down, as we move from left to right. So we can see just with this sketch of a we know it's a positive cubic and probably expecting it to look like this. Okay, here is where it is. Okay, increasing. Oops, if I can write. Okay, there and also there. Okay, and at this point here is where it is decreasing. So the key really is to find the point at which it is changing from increasing to decreasing or decreasing to increasing. So we want to find those stationary points. Okay, so that's our first thing we need to do. Okay, so our stationary points occur when our derivative, f dash of x, is equal to 0. So that's our first step. We need to find the derivative and let our derivative equal 0. Okay, so we end up with 3x squared plus 4x minus 3. Pardon? Oh, yes, yes, my brain a little bit off, obviously, so let's correct that. 8x, thank you. Okay, so we'll let 3x squared plus 8x minus 3 equals 0. And solve that. So let's see if we can factorise it. So we need to multiply to give negative 9 and add to give 8. So that's going to work. That'll be positive 9 and negative 1. And so we find our stationary points will occur when x is equal to negative 3 or a positive 1/3. Okay, then we do our gradient table, and if we were to put our value of -4, so we're picking points either side of our stationary points, so -4, 0 and 1 are nice convenient numbers to use, putting those values into our derivative, and we'll see that at -4 our derivative will be positive. Okay, at 0 it would be negative, and at 1 it would be positive again. And so we can see the shape of our graph is as we expect it to be, being a positive cubic. Okay, so where is our function increasing? Well, f of x is increasing when x is less than -3 and also where x is greater than 1/3. Okay, because that is where those are the values of x for which our gradient is positive. F of x is decreasing when x is between -3 and 1/3. Okay, so once you've written that down, I'll get you to make a start on that by finding the derivative and then working through to find the coordinates of the stationary points. Okay, depending on how you went about doing that, whether you expanded it and then differentiated it, or whether you used the product rule. In one sense, using the product rule probably allowed you to factorize it a bit easier, so to get to this point here. That ideally is having it like this, because then you can let f dash of x equal 0, and so 3x plus 6 minus a equaling 0, meaning x is equal to a, or solving the other one, we end up with x is equal to a minus 6 over 3. Now, I'm just thinking, for something like this, it may even, the best way to do it perhaps is even to use the calculator. Okay, so bring that across here, and so we can find the derivative, okay, a couple of ways. If we go to action and calculation, okay, action and then calculation. Diff means just to differentiate, so you can use that and then put in your function. So what have we got? We've got, so we need to put a couple of extra brackets here. So is that not? Okay, this doesn't work for me. I'll try and reopen it. Okay, now it's working. Right, so we've got x plus 3, close brackets, put in another bracket, and then it's x minus, now I need to go to the keyboard to bring up variable a, close bracket, and then squared, and then close the brackets around it all. Okay, and of course it's giving it as a fully expanded expression, but we can go transformation and factor. Yeah. And then just highlight and drag that expression so you don't have to retype it in there, and then press EXE, and it gives us our derivative factorised. The other way you can factorise is just on the keyboard in Math 2. You can see there is d over d in the space in the variable you want to use. Okay, so that also will allow you to do the derivative. Okay, so d, and put in the variable x, and then we can insert that in, and it does the same thing. Okay, so we've got our derivative, and we can then of course use the solve button, so we can just solve our derivative equaling 0, but we want it as its exact value. Okay, so we've got those two solutions, x equals a or x equals a over 3 minus 2, which is the same as a minus 6 all over 3. Okay, so those are our values for where our stationary points are, but we want the coordinates of the stationary point, so we really want to be able to put those back into the original function. So probably the best thing to do is just to put our original function back down there and just replace our x with a. Well, it's actually not going to be too difficult, is it? Because when we replace that with a, we can see that second factor there will end up with 0. So we're going to end up with 0. So we can see that if x equals a, or rather f of a will equal 0. So we have a stationary point at a0, and we want f of a minus 6 over 3, and so we'll do the same thing. So we'll replace that one. So replacing our x with the other value, and so we get our other y value. Actually, I wonder whether that can be simplified. Expand. And just have to factor that again. Okay. All right. So the calculator doesn't always necessarily give it in the best form. So you can see when we just substituted it in, we got those two terms. So we've got that sort of two factors of 2a over 3 plus 2 squared times a over 3 plus 1. Expanding that gave us this cubic, and then just going factor again gave us something a little bit more friendly. So we could even rewrite that a minus 6 over 3, and then 4 times a plus 3 cubed over 27. Okay, I mean either of those really are correct. So those are our stationary points. Now what is the nature of those points? Well, that's where we need to do that gradient table again. Okay. Now, in terms of finding the actual nature of those points, it's going to be a little bit hard when we look at that to think how can we find the nature of the points. We don't exactly know where they are because of the value of a, but we do know that a is a positive real constant. So since a is greater than 0, we'll just let a equal positive 1. Okay. So by doing that, we'll be able to get the nature of those stationary points, whatever the value of a is, knowing that it's positive. Okay. Choosing this value allows us to go through a process to find the nature of them, even though the actual position of them could well be changed. Okay, the nature of them would stay the same if a is positive always. Okay, so we're going to let a equal 1, which means that we can use, so 1 minus 6, that'll be negative 5 over 3. And then putting that into this one here, so that's the a minus 6, so a is 1, that makes 4 cubed 64 times 4 over 27, so that is 256 over 27. And the other one, well, it's pretty simple, that's just going to be 1, 0. So then we'll use our gradient table, negative 5 over 3, so we'll go negative 2, negative 5 over 3, 0, 1, and 2. Now, if we put in to our derivative the value of negative 2, that's going to make our derivative 2 minus 1. Sorry, negative 2, that's going to be negative 3. That'll be 3 times negative 1, that's negative 3 minus 1. Yeah, okay, so it will be positive. -3. Is it? -2. Times y. Oh, yes, of course. So that's going to be positive. That's going to be 0. Putting 0 in there. It's going to be -1. It's going to be -0 and positive again. Okay, so our point -5/3, 256/27 is a local maximum, which means that in terms of our value, in terms of our variable a, that corresponds to that point, a minus 6/3, etc. So that's our local maximum, and the other one, which is 1, 0, which corresponds to A0, is a local minimum turning point. Now, the other part of the question is to find the value of A if the straight line with y equals 5x plus 15 intersects at the maximum turning point. So we want to then use that point. So we know we have, if it intersects at, so y equals 5x plus 15, then we can use that point that we've got here. Okay, a minus 6/3 and 4 times a plus 3 cubed over 27. Sub that into y equals 5x plus 15. And that will give us our values, because our x coordinate is in terms of a, our y coordinate also is in terms of a, so we can substitute that in there and we'll be able to find it. And the best way to do that, again, just using our calculator for this type of problem. So I'm going to go solve, okay, our y value equals 5 times our x value, which was, let's type it back here. And when you're using the solve thing on your calculator, if you're using a variable that is not x, in this case is a, you just need to put a comma and then the variable a, just to tell the calculator we're solving for a. Okay, and so it's, because it's a cubic, okay, it's giving us 3 solutions. A is -3, or -3 root 5 over 2 minus 3, or 3 root 5 over 2 minus 3. Now, because at the start it says that a is a positive real constant, okay, then that last solution can be the only one that is applicable. Okay, so yeah, definitely a harder type of problem. But that sort of problem, you're better off trying to use your calculator, learning to use your calculator to help you solve that kind of problem. Okay. Probably the trickier part was just being able to see that in order to find the nature of those points, it's just taking that value of just a hypothetical value of 1 for a. Okay, being a positive value so that you can see what the nature would be. Okay, because it would still be the same if it was, say, a value of a equals 2. Okay, but yes, a difficult problem definitely to work through if you did not have your test calculator. Okay, so learning to use it in these sort of situations is a good idea. Okay, that's it. I'll get you to just basically just to keep working through exercise 8b. Okay, just getting a bit of practice at finding your stationary points, finding the nature of those stationary points. Probably later on in that exercise there'll be problems sort of similar to that one we just looked at there. I think, yes, looking at, say, questions sort of 17, 18, 19, those type. So after doing a few, maybe it's worthwhile doing a couple of those just to have a bit of practice. Okay.